All right. I'm glad Klaus allowed me to come here because I was too slow getting a spot on Meetup. But here I am. And now I just need my clicker and right. So, my name is Robert Schimkowitsch. I work on control center systems for hydroelectric power plants with 25 years of experience, 15 with C++ and Qt. It's mostly desktop stuff, more toward the GUI side, and I can use C++23 at work. Yes. Which means that all the standard library things that you see here have been tested in my production code. I'm also co-organizer of C++ user group Vienna. Okay, there's this subtitles. Thanks. I'm also co-organizer of C++ user group Vienna. And if you ever go there, come join us at one of our events, no matter if you want to watch a talk or give a talk or just have a drink with us. Over the years, I have solved similar problems more than once. And this has given me an appreciation on how my own coding style changed over time. So when I now see some older code, my instinct is to think, how would I write this today? So imagine you are me, and you have just stumbled over this piece of code. So just give me your feeling. Who likes this style of coding? I don't see any hands here. And who does not like this style of coding? I'm with you. I don't like it, and I'll tell you why. This function interleaves the core functionality with error handling, making it really hard to see what the function does at a glance. Also, the return value is not the return value. It's a success flag. The return value is at the end of the function, the byref out parameter. We are not going to mix those two up, are we? Use exceptions, and you could have something like this. Except, of course, you would have to throw somewhere up the call stack, and you'd have to catch somewhere down the call stack. And if you forget that, the application crashes. And also, should we use exceptions for domain errors? I'm not sure. Then there are people who can't use exceptions really, or don't want to use exceptions. So I guess this is not for everyone. So back to square one. Other ideas? We like classes, right? So why not make the error flag a class member? Now everybody can access it and every function can check it. Isn't that great? Of course, we just moved the checks around. We didn't really solve anything. And congratulations, we have just created our own little dependency hell. Because every function now depends on that single flag. This is called shared mutable state, and it's poison to local reasoning and thread safety. So let's take a step back. And let's just fix the return type issue. And I combine the return parameter and the success flag into an optional of bool. So now the optional tells me, is there a value? If no, then that's failure. And if there's a value, I can use it. And then I throw away all my if statements and let optional do the work for me. This way, the sequence of the function is clear and plain to see. And optional takes care of the error handling. I cannot forget it. This is a monadic operation in action. I have 3 goals for this talk. The first is that after this talk, you understand what functors and monads do, not what they are. That's something different. And that includes some practical usage experience with how do I pass my callables, how do I fix the first compiler errors that I'm going to get. There will be plenty of examples. And the next one is how to use the monadic operations that come with the standard library. That includes ranges, optional, expected. And I want to give you more material. If you want to dig into this topic, there will be a link at the end of the presentation. You will find all the source code there, Compile Explorer links, and links, materials, articles, videos. Of course, it's slideware. So all code on the slides is available also on the GitHub or in the Compile Explorer. Please use the code from there, not from the slides, because this code is optimized for readability here. And also, I have children. I managed to get rid of the dinosaurs, but there might be a unicorn or two hiding in the slides. All right, we'll start with functors first. They are simpler to explain than monads and similar to use, so it's quite useful to start with functors. Now, my first question to you is this a functor? So who says, yes, this is a functor? And who says, no, this is not a functor? Well, most abstain. In a way, both are right, because the term functor is overloaded and it has multiple meanings. This is something I would call a function object, an object that can be used like a function, but this is not the functor we're looking for. But before I tell you which functor we're looking for, I will start with a little story. Once upon a time, there was a sequence of code. It consisted just of two functions. One calculated the area of a circle from a radius, and the second one formatted this area as a nice string. They were combined, so I could pass the radius and would get a nicely formatted string. And everything was good. Then a developer brought a vector of radii and thought, I'd like to have a vector of strings for that. No problem, they said. We'll just make a loop. And inside the loop, we will do pretty much as before. But then one of the functions said, this does not feel right. I'm sitting here together with code that has nothing to do with me. It knows nothing about radius or area. I fear we have violated the single responsibility principle. And when I asked the seer what he sees in the future, he just said, code duplication. How much better would it be if somebody could magically transform us poor functions so we can handle vectors? Like we would have a new function created from the old one, and we would pass the old function as an argument. The new function would accept whatever a vector of whatever argument type the old function accepted, and would return a vector of whatever argument type the old function returned. So for the format area, I would take, which takes a double and returns a string, we would now accept the vector of double and return a vector of string. Then we can combine those two functions, and now they can handle vectors. The vector aspect would be implemented only once, even if you replaced those functions. You've just seen one way to use a functor. I'd like to show you a different one that's more widely used and maybe more practical. Let's think of a functor like a container, maybe, or a magic box. Put in a vector of building materials. Send in a worker with a plan, just one worker. And take out a vector of houses. And how would we implement that? With a class. And this time the class holds the data we want to transform as a member. This is not necessary for a functor, but it's often convenient. So now we pass our function that we want to use to transform the data into a member function called transform, for example. This will apply to all items in the vector. The result is a new functor, so we can immediately repeat the process in the second stage of the pipeline. Again, the vector part is only implemented once. You have now seen two approaches. Both are functors and both solve the problem I showed. But what goes on in detail? And we will start just from the radius. So we can calculate the area and we can format the area. Nice and easy. Oops. Should I be worried or is it all right? Okay, let's look at the vector side of things. We can construct a vector from a radius or multiple radii, and we could do the same for area and string, but that's not what we're interested in. So let's start again from the vector of radii. Using vector, using the function that handles a single item. And then we do the same to get from area to the formatted string. The nice thing is we don't have to stick to vector. We can just replace it and use optional here. The functions that we put in there are the same. We don't need to change them. I'll add a little theory. So there's two rules that functors have to follow. The first one is rule of composition. We could compose our function so that we only have a single function that takes a radius and outputs the string right away. Of course, we could also pass this composed function to our functor, and we would get a vector of strings. It has to be the exact same vector of strings as if we followed the pipeline step by step. The second rule is the rule of identity. We need to be able to preserve identity. What do I mean by that? Let's use a different function now, std identity. For those that don't know it, it just takes a parameter and returns it unchanged. Sounds silly? Please play along. Because of course, it's a good function, we can pass it into our functor. And the result that we get must be identical to the input that we gave. Does that sound silly? It has real implications. It means the functor cannot use internal or external state to influence the result. It has to just follow and use the function that it's given. So in summary, functors provide a mapping between categories like from single items to vectors to optionals and to other things. And they have to preserve composition and identity. They can be implemented in different ways. We have seen two different ones. They don't have to be objects, although they will often be in practice from the ones we know from the standard library, for example. They don't even have to hold the value. Our first functor didn't hold the value, and it worked just as well. I have used vector as an example to show you the benefits of using functors, but of course it doesn't have to be vector. It could be any container, or it could be any iterable range, or whatever. And of course, we don't want to implement such a functor ourselves. And we don't have to, because the standard library has it. It's called std_ranges_views. Let's look back at the vector example, specifically at the classic implementation. And down below is the implementation using std_ranges_views. Let's walk you through that. So the view offers a transformation function, transform, and this one has two parameters. The first one is the input, an input value, and the second one is the callable that we want to apply to this input. Now the return value of the transform function is the output, which becomes the input of the next stage of the pipeline. However, this notation with inner transform, outer transform is a bit inconvenient, and it gets downright confusing as the pipelines grow longer. So the pipe operator to the rescue. This way, the pipeline is expressed in a much more natural notation, and it does exactly the same thing. So how does that work? We start with our input, and the pipe operator will basically inject this input as the hidden first parameter of the transform, if you go by the logic of the first example. The result of the first stage of our pipeline becomes the input of the second stage. Nice. Now there are two questions. What do we actually return? And what type is that view? We will answer the second question first, because it's important to know that views are not a container with results, They are more a recipe from a cookbook. They are not a cake, but they will tell you how to get cake. They typically don't own the data. So if somebody steals all your ingredients while you're baking, that's undefined behavior, or at least you will not get cake. And they are lazy, which means constructing the views costs almost nothing, probably memory. But when you start drawing out data from them, then they will provide the data on demand. And this is the actual output type. It varies by compiler. This is MSVC, but it doesn't look much prettier for GCC and Clang. And auto is pretty much the only way to use it in practice. This has some implications. Because, of course, you can write a function that returns a view, but it will have auto as the return type. That still does not mean it's a template function because it's only the return type and it's actually well defined. We're just too lazy to type it. So when we start using such functions from multiple files, we can expect trouble. So 3 recommendations. First, mark such functions inline. Don't overuse them. And try to keep the scope small where you use them. So you still have a view on the ownership of data that goes into the view. The alternative is to return a container. And that's easy with C++23, stat ranges 2. It converts to any container that fulfills the requirements of stat ranges 2. That can be a standard library container or a third-party library container. This way we have a clean API and we can separate declaration from definition again. What we lose is the laziness, because this last line of code has to execute everything that's needed to fill our container with data. So in summary, views are more like the recipe than the cake. They typically do not own the data, so be careful about changing it while you hold a view on it. You typically use auto with them, and they evaluate lazily. But there are traps. Well, of course there are. It's C++ after all. So who can spot the bug in this example? And now I forgot to ask if we have a microphone for the audience. I will give you a hint. Okay. So what happens here? We have a pipeline with 2 stages, and the first stage calls get nearest entry, which returns a C entry, just a simple struct. But in the second entry, we just want to get the text, nothing else. So we just take the member. What we take is a reference to the member, but the C entry we got in the first stage is a temporary. It goes out of scope, and poof, we're done. We hold a dangling reference, and that's it. Well, dangling references are nothing new, and they're not specific to stat ranges view, but maybe they are a bit harder to spot in this notation, so be careful and always use a sanitizer. You might have noticed that passing callables is an important part of using functors, and the same goes for monads. When I started using this coding style, I often had difficulty finding the right way to fit my functions into the functors that I wanted to use. I wrote complex adapters, and sometimes I just threw up my hands in despair and went back to classic imperative coding. I'd like to spare you some of the trouble, so I will show you a few ways to feed your functors. We've seen the use of free functions, and they are easy to use and straightforward as long as you don't have overloads. We will come to overloads later. Static functions of classes are pretty much the same. You just need to use the class name for qualification. And inline lambdas are a very direct and simple way to make use of functors. You just write the code where you use it. It's, of course, most useful if the code is very short and you don't want to use it multiple times. But they are, for example, a good way to get rid of overload compiler errors. So if you have an overloaded function, having a wrapper lambda around your function will actually help the compiler pick the correct overload. So in most cases, that solves the problem. Another typical issue is I have a function with multiple parameters. What do I do? My functor only gives me one. Well, I write the lambda with one parameter and the rest come via capture list. We want to call member functions of classes maybe. So let's say our functor gives us an object instance and we want to call a specific member function. We can write the wrapper lambda and in there we just call the member function and return whatever it returns. The other way around would be if our functor gives us a value and we want to pass this value into a member function of a known object instance. Again, we can use a lambda for that. If you want to use a lambda multiple times, or just give it a name for readability, you can use a named lambda. Another interesting option is injecting behavior. If you want to inject behavior from the outside, for example, you have a 5-stage pipeline and you want to give the user of your function the option to change stage 3 of it, you can use that function. It wraps any callable. The template arguments tell us what the return type and the parameter types are. And it gives you a lot of flexibility. Wait a second, I'm one ahead. This is the function object, which is pretty similar to the lambda. Sorry, I'm now in sync again. So this is the function object, which is very similar to use compared to the lambda, but it gives you more flexibility. Now we come to stat function. I should have made the font bigger. It wraps any callable, as I said. And the template arguments tell us return type and parameter types. And then we can just pass it in our functor. Of course, we can also pass our callables as template arguments. And if we want to check the signature, we can use the stat invocable concept. Templates have typically better runtime characteristics, but they come with some complexities because you cannot just separate declaration from definition that easily. So in summary, there are many ways, and there are actually many more ways. If you look at my example sources, you will find a few more options, mostly from the standard library. But if you use lambdas, you have a good basis. And if you add that function to inject behavior, that should get you pretty far. Now that we have talked about functors and we also know how to feed them properly, we can talk about monads. Because monads have all the properties of functors plus something extra. Again, I'd like to start with how a monad helps us solve a problem. We have a node in a tree-like structure and it has a function called getChildren. It's not important how that works exactly. What's important is there could be multiple children. So we get a vector of nodes. If we want to repeat this process and get the grandchildren, that's not going to work because getChildren is not equipped to handle a vector. Functors have been pretty cool so far, so maybe they can save the day again. Let's try. So we do our transform and we get a vector of nodes. Our next transform is not going to be happy about that. So what do? We invoke monad magic and join, which means we flatten our vector of vector to just a vector of nodes. This allows us to continue. And we can transform again. And we can join again. So for practical purposes, monads are functors with the ability to unwrap one level of nesting. I know this is pretty hand-wavy, but I'd rather stick to practical examples than go deeper into the theory than that. They typically cannot unwrap the last level of nesting. What would you unwrap a vector of int to? The rules for composition and identity still apply because they are functors as well. And the functions transform and join are often combined into a single function, which can vary by name. We will see a couple of examples later. But let's leave theory behind and look at examples. It has been said that a compiler is a tool that takes files as input and produces diagnostics as output. Let's forget for now that it also might produce usable object files and focus on getting and printing those diagnostics. So we have a function to print a single diagnostic. Then we have a function to compile a single file, which gives us, of course, a vector of diagnostics. Would be boring if we had only one error. And then, of course, we might want to compile multiple files. So I just wrote a function that compiles all files, that gives us all files in the project, whatever that means in detail. And this would be my classic loop style implementation. So we start looping the projects. Get the files in the project, loop the files, get diagnostics of a single file via compile, loop the diagnostics, and print each of them. Who uses code like this in their code base? All right, so what would we replace that with? Let's try this one. So using state ranges views, we would start with the projects. Then we would transform them into files, which gives us a vector of vector files. So we join, making it just a vector of files. Now we can pass that one to compile, which gives us again a vector of diagnostics. So again, we join. Having now a vector of diagnostics, we can simply loop and print. So here are both versions side by side. What do you think? Which one makes the intentions of the author clearer? Now the question is, do they behave differently? If I start drawing out the data right after, then in fact, no, they call the same functions with the same parameter in the same order. Details will vary, of course. I'd like to sidestep a little and talk about the topic of using functors and monads and specifically ranges views safely. And pure functions are a key. Who knows what a pure function is? Okay, for all the others, I will explain in a minute or two. But let's first start with a motivating example again. This time we start at the bottom with a vector of numbers. And what we want is a view on those numbers multiplied by 2 in our case. So I've made a function that does that. The function is now above. Get multiplied view takes our input, a vector, and a multiplier. Inside, we use a simple lambda to do the multiplication for a single item. And the multiplier gets passed by lambda capture. And then we return a transform view using that lambda. In our calling function, we just print the output. It doesn't matter how. And what would we expect? We started with 2, 4, and 6. So that would, of course, be 4, 8, and 12. What? That can't be right. Yeah, unfortunately it is. And the numbers will change every time you change compiler or whatever. So we have a problem here. What is it? First, we pass the multiplier by value, which by itself is fine. Then we capture it by reference, which is already a bit fishy, but would still work. But then we get the laziness of the transform view, which only evaluates after we have left our function scope. So we are sitting here with a dangling reference. This is just one example from state ranges views, but in general, we have to be aware that functors and monads control when our functions get called, how often our functions get called, and in what context our functions get called. So how do we avoid bad usage of our functions? I basically see two choices. We can study the fine print of our functor or monad of choice and hope that there is a documentation and the guarantees don't change over time. Or we can protect our functions by making them purer, and that's the path I'd like to explore. So what is a pure function now? It has two properties. First, it always returns the same result for the same input. And second, it has no side effects. So what does that mean? Same result for same input. Let's say we have a function which takes some inputs and an output. Assuming you had infinite memory, could you replace it by a lookup table? If the answer is yes, we are good on that. What does no side effects mean? Basically, we don't write to outside memory, and we don't trigger other side effects such as I/O or similar. Pure functions have a lot of advantages. They're easy to reason about. You just need to look at the function to understand it. And in the calling code, you know that this function, that you see everything that this function does or needs. It's easy to write unit tests for them because the unit test can implement a part of this lookup table to check if the function actually returns what it should. Also, the unit test does not need to check for any weird side effects that the function should or should not trigger. And if they are really pure, they are inherently thread safe. Now let's have a little quiz. I will show you some functions and you tell me whether they are pure or not. So let's start with stdmax. With int and int, two values, both integers, no custom comparison. So who thinks this is a pure function? And who thinks this is not a pure function? Okay, majority wins, this is a pure function. If you, by the way, if you have other opinions, I'm happy to discuss that after the talk, because it was quite interesting to have a discussion in my user group about that. The next one is stdfill, the function that we can use to fill a container or range with values. Who thinks this is pure? Who thinks this is not pure? I'm with the majority again. This is not pure because it writes to outside memory. Std chrono system time now. Who thinks this is pure? Who thinks this is not pure? Well, it has no side effects, but you can't replace it with a lookup table. Std sin with double, calculating the sinus. Who thinks this is pure? And who thinks this is not pure? Yeah, it depends on global state because it depends on the rounding mode, although I'm not quite sure now if it may not be different per compiler in some ways. Next to last one, stdups, getting you the absolute number of int. Who thinks this is pure? And who thinks this is not pure? Well, it's practically pure, but what happens if you pass int min? It's undefined behavior. Can you call it pure? I had long discussions on that, so I don't have a clear answer. Last one, std any of, that we can use to check if any item in a range fulfills a predicate. Who thinks this is pure? And who thinks this is not pure? Well, I would say this was a trick question because here we completely depend on the predicate for a start. If the predicate has side effects, so do we. But even if the predicate is pure, we are using iterators which read outside memory. Now, can we guarantee the lookup table thingy? I'm not sure. But what I wanted to show you with this quiz, purity is not a black and white thing. There's a lot of gray areas in between. So while pure functions help us write safer code, there's different degrees of purity. I take the practical approach and say, make your functions as pure as is reasonable for your use cases. Which brings us back to our initial example. So one way to look at it is to say this lambda is not pure, it depends on outside state. Can we make that better? Well, we can do our capture by value. I still would not call this entirely pure, but it's pure enough to fix our problem. In the examples so far, we have not used any function that indicate failure, of course, for simplicity. But in real-world code, we typically have to handle error cases as well. And if we don't want to use exceptions, at least not for domain errors, we need other options. So in the following section, I would like to compare a classic value-based error approach with stored optional. This is our example. So we have some kind of storage structure, a database, or whatever, and it contains very different kinds of data, like trends, images, tables. Looking more closely at the table, we can identify the column by key or index. We can do the same with the row, which gives us a cell. Now, we can look at the value in the cell and ask, is it a number? Doesn't have to be. If it is a number, we can ask if it's negative. So this is what we want. A function which tells us if the numeric value of a table cell is negative. What could possibly go wrong? Well, the key to the database might be invalid. The element might not be a table. Row or column index might be out of bounds. The value might not be numeric. And finally, we have one step which does not fail, at least not for the type we are using. And these would be my helper functions in the classic implementation. So we have a function called getElement. We pass some database and a key for an element. And we receive our element as last byref out parameter and the bool success flag. I've seen those a lot in older code and I hate them, because they make it impossible to compose functions, and they are often not as efficient as they could be, calling more constructors and destructors than necessary. But that's what we have. So let's continue on with getTable, which again returns the data as byref parameter and returns the bool success flag. And then we have the same for getCell and getNumeric cell value. Does anybody have a flashback here? We have seen this one before. And everybody loved it. So this is how we call the functions. We create an element on the stack, and then we ask getElement to fill data into it. And if getElement is unable to do so, it will return false, and we ourselves exit our function, indicating failure. Same for getTable, create on stack, ask to fill, early exit on failure. And so on and so forth. Finally, in the last stage of the function, we can check if the value is negative and return with success. So who has code similar to this? Oh, that's not so few. I had hoped for fewer. So let's try to find a more monadic declarative way. We change our interface for the helper functions, and instead of bool, we return optional. We combine the actual return value and the success flag into optional of our return value. Now, if a function fails, it will just return an empty optional. And if it succeeds, it will return the value inside the optional. We do the same for getTable, getCell, and getNumeric cell value. For the sake of completeness, I added an isNegative function, which of course I could implement as an inline lambda. But the interesting part here is it does not return an optional of bool because itself cannot fail. So we just return bool. And then we start the chain of operations with getElement. getElement returns an optional of element, and this allows us to continue our pipeline conditionally using the function endThen. EndThen will only execute the callable that we pass as the only argument if the optional contains a value at that point. If the optional is empty, we will just bypass the function. Since we are working with values that may be there, this is also called the maybe monad. So let's assume that getElement and getTable both succeeded. We now have an optional with a valid table inside. Quiz time. There is no join here. Why do I still call this a monad? Does anybody have an idea? Okay, that was actually just an excuse to get a drink. But if somebody would have answered, I'd be happy for that. Anyway, so we called getElement, which returns an optional of element. We call the next function getTable, but this does not take an optional, it just takes an element. So actually, we have unwrapped one level of nesting like a good monad should. Now, in a way, endThen is a combination of transform and join, like I mentioned before. But what if we only wanted to do a join with optional? There is no join in optional, by the way. So let's say we have an optional of int, and we would just like to unwrap it to optional of int. How could we do that? Does anybody have a suggestion? Yeah, I see a hand here. Oh, good one. I didn't even need to post my hint. So we can just pass identity function to endThen. endThen does both join and transform. But since transform with identity comes to the same result, it's like we only did join. I'm not sure I would recommend this in production code, but I think it illustrates nicely the guarantees that we get from monads. Back to our code. So we pass the table into getCell. Now getCell needs a second parameter, the cell location. And here we can just use a lambda with the lambda capture to pass the cell location. Let's assume it was a bad location. Not like this one. It was a bad location and our optional is now empty. What happens to the next function? It gets bypassed because endThen will simply bypass the function if the optional is empty. We still get an optional of the correct type, so we get an optional of int, but it's just as empty as the input was. Now, is negative does not return an optional, so we cannot use endThen here. Here we use transform, just like for ranges and views. It changes the value inside the optional if the optional has a value. If not, it just changes the type of the empty optional. So what can we do with optional? The basic operations, we can check the value. We can access the value if we have one. If you try to access the value of an empty optional, you get an exception. We can simplify this a bit by moving the initialization into the if statement. This way, we can both assign and check at the same time because operator bool of optional tells us whether the optional holds a value or not. We could simplify further if all we care is falling back to a default value if the optional is empty. And back to the code comparison. So let's have a little poll here. Who prefers the classic version of code? You will laugh. In my user group, some raised their hands. And who prefers the monadic version of code? Thank you. Now, we have a pipeline which will fail gracefully if it fails, but what if we want to log failure in some way? And then has a sibling function called or else. It works exactly in reverse. So it will only call the function if the optional is empty. Since we use empty as indication of failure, we can use that to trace failure. Why is this a template function? Because the log function needs to return an optional of the correct type. Since it does not get a parameter, it cannot deduce the type, so I just tell it what optional to return. Now we have a problem here, because let's say we had our error in getCell. We can catch the failure at the end of the pipeline, but we have zero error context. We just know that something failed. And that's not typically something you want to read in a log file. Something failed. So there needs to be a better way. StdExpected is a new type in C++23, and it's very similar to optional. So instead of optional, we change our functions to return expected. Now expected has a second template argument. The first argument is same as optional, the value. The second argument is alternatively error information. Now, if a function fails, I can return an unexpected, and I can choose my error type. So here I created a custom simple error type called CR, which takes a message as the constructor parameter. I can also, inside the constructor of CR, capture the whole call stack with stack trace. So if you're interested in that, look up that stack trace. Exists since C++23. And well, if our function succeeds, we just return a value as before. The chain of operations is identical. So, and then works the same way. If our expected holds a value, it will call the function. Now, if we have an error, our expected now holds an error information, is not empty. The next end then will skip the function like before with empty optional. And at the end of the chain, we can capture the error information because our log function now receives the error information as parameter. So we can now actually log some useful things. So for example, if getCell had an error, we will write message and stack information, whatever, and that gets passed down to log, and then we can do the logging. Now, the log function also returns an expected, and we can choose, do we just pass through our expected? Do we amend and enrich the error information in some way? Or do we even fall back to a valid value? Although I would probably not do that in a function named log, it might be a bit surprising. Usage is very similar to optional. We can check if it holds a value, we can access the value, and now we can also access the error. Expected always holds either value or error information. Again, we could move the initialization directly into the if statement, but this is strictly less useful for expected because now we cannot access the error information in the else. But if you just care about the happy path, that's fine. Well, and there's value or, like for optional, also for expected. Error or exists as well, but it's, I would say, more for fringe use cases. If you have a fragmented code base or you use third-party libraries which use expected in their APIs, you might end up with different error types. So we might have an expected with CR, but we want an expected of my error so we can pass it through our own APIs. All you need is a conversion function that can convert CR to my error, and then you call transform error. If the expected contains a value, no value will change, only the type will change. If it contains an error, the conversion function will be called and the error will be converted. We have seen how optional and expected allows us to have a pipeline of functions where any function might fail, and we want to ensure that we get through the whole pipeline well and in one piece. Sometimes you want the exact opposite. You want to call a sequence of functions and you want to take the first result that works. And this is easy to do with optional. Let's say we start our application and we want to determine the UI language. And we have given our user 3 ways to define it. So they can specify it via command line. They can use the registry or something similar. They could set an environment variable. And if all else fails, we have a fallback value. This is how we would write it using std_optional. In this pipeline, the first function that provides a value wins. So let's assume that getLanguage from command line failed. Our optional is empty. Because of that, or else will call the next function, getLanguage from registry. Let's say this one is successful. Our optional now has a value. The next or else will bypass getLanguage from environment, so the value remains unchanged. At the end, we can provide a default value, so had the optional be empty at that stage, value or would have provided the default. Maybe someone of you noted that I put monad in quotes in this section. Does anybody have an idea why? Andreas? Yeah, I think I'll explain it in slightly different terms. Because on the one hand, we have an axis where we transform things. So we not only transform values, but we actually transform the types contained in the optional. In the other dimension, we do unwrapping. So the join unwraps us. We know we don't have a join, but we have end-then, which combines both axes of this table. So with end-then, we move across this table, we change types, we change wrappings. With or else, there's no movement. We stick to one cell of this table and we never get anywhere else because the first function defines the type we are using. There's no translation in any direction. This is not a monad. I'm not sure I would call it a monadic operation. I would call it monadic style operation. But it's still useful, so go out and use it if you feel it's the right one. One of the first obstacles you will encounter when you start using monadic operations are compiler errors. My personal experience is I spend slightly more time on compiler errors, but less time on runtime errors, which is a nice trade-off, I think. But still, I don't exactly love fixing compiler errors, so I wrote down a little cheat sheet for myself to fix the most common ones quickly. So we have a little pipeline and it does not compile, and this is what the compiler tells us. The dreaded wall of text, MSVC again. But GCC and Clang are not that much better. So I found it useful to focus first on the beginning and then on the end of the message, because in the beginning we find that some matching call operator could not be found, and in the end we find something about could not deduce template argument. The one with the matching call operator is pretty much the same in GCC and Clang. It's also pretty much on the start of the message. Now let's look at the cheat sheet. And we will go from top to bottom. The first question we have is, which part of the pipeline does the error happen in? And if you have trouble pinpointing that, you can split up the pipeline until you know exactly at what stage of the pipeline the error happens. Then, when you know where the error happens, you can ask, is the function that I used there maybe overloaded? If it is, use a wrapper lambda. And this, by the way, is the error we had in our example. You could, of course, alternatively change the function and remove it from the overload set, but that should probably not happen just because you want to fix a compiler error. That should be a design choice. Does the function accept the correct type? If you use a lambda, try to make the type explicit. That way, the compiler error moves inside the lambda in many cases, and the compiler will give you a better output. The same applies to return type. If you have a lambda, make the return time explicit. That will help the compiler give you better errors. Specific for std ranges views, you might miscount the number of joins, so function gets vector of thing instead of thing, or vice versa. And do you maybe use any const views anywhere? Maybe in a function that just takes them as const reference or something like that? Just don't. That does not work. It's not designed that way. Views are semantically references, but they are meant to be used as non-const values. And specific for optional or expected, you might sometimes mix up and then and transform. So function gets thing instead of returns thing instead of optional of thing, or vice versa. So in my experience, this covers a lot of the most common compiler errors. And if you go through this list, you should be able to fix them quickly and efficiently. Let's now leave the path, the comfortable path of monads provided with the standard library, and try something new. Let's write our own monad. We have studied the optional example in detail, and there's something pretty similar in the language to optional, a pointer. It can be valid or it can be null. So let's write the pointer monad. I will reuse the example from optional. So our goal is still to determine whether the numeric value of a table cell is negative. And instead of our classic helper functions, we changed them to return pointers. You might notice that they look now pretty similar to the optional versions. The classic pipeline we replace with something like this. I move the pointer initialization into the if statements. That way it fits on the slide. But why not? I mean, of course, why not? But we will see why not. Now, I also changed the return type of the whole function to optional of bool because somehow returning a pointer to bool didn't feel right. So this is how things would look with our custom pointer monad. So this is the sequence. We call our first function, which returns a pointer, and we wrap it immediately into our helper class called cptr. Like optional, cptr offers us a function called and then, and we can pass a callable. It follows the same logic as optional. So we pass get table ptr, a function, and we expect it to return a pointer, valid or null. The same for getting the cell and for getting the numeric value of the cell. Now the transform here is interesting because cptr does not have a transform function. How does that work? Because actually get numeric cell value returned an integer, and again I found it pretty useless to return a pointer to int. So I just returned an optional of int. Now you can see that we can seamlessly transition from pointer to optional monad and get our final result as an optional. Now, how is that implemented? So we create a class. I named it cptr, and it acts in most ways like a pointer. Of course, we want to support different pointer types, so it's a template class. The template argument is constrained to be a pointer type using C++20 concepts. We have a default constructor which constructs a null pointer object, and we have a custom constructor where we can just pass a pointer. Then we have some convenience functions that give us some pointer-like behavior. It's not a complete set. We could extend that, but it covers the basics. And then we come to the fun part, the monadic function. Being consistent in naming, we name it and then, and it takes a callable as a parameter. The return type is unknown yet, so we have to use auto at this stage. And here's the implementation. So first we have our template arguments. tptr is the pointer type of the pointer that we currently hold in our class as a member. And tcall is the type of the callable that we want to call. Inside the function, we create two helper types. The first is tref, which is the reference type matching the pointer type. And the second one is tret. I'm not sure the naming choice was great, which is the return type of the callable, and we can get that using std invoke result t. Here we will pass the reference as the parameter, which means the functions don't need to check for pointers anymore. They will only be called if the pointer is valid, and then they get it as a reference. Then we have two branches. The first branch handles callables which return pointers. We check our own pointer. And if the pointer is valid, we invoke the callable. We forward the callable and our dereference pointer via std invoke. Then we wrap the returned pointer immediately into cptr. That way, the next stage of the pipeline can immediately call and then again. If our own pointer was invalid, we construct a null pointer object of the correct type, cptr, and return it. The second branch handles return types which are not pointers. And for now, I only support functions which return optionals. Could be extended. This is the check to see if the function actually returns an optional and not something else. Again, we invoke if our pointer is valid. This time we return the result without wrapping. It's already an optional, that's fine. And if our own pointer is invalid, we return an empty optional of the correct type. I have highlighted the differences between the two branches. Wrap pointers into cptr, but leave non-pointers as they are. Of course, we could handle other cases as well, but for now that was enough. And I'll just add a static assert at the end so that if anybody passes us a function which does not fulfill my requirements, I get a nice compiler error. And again, here is how we use the pipeline. Of course, it could be extended. We could add transform. We could support functions which already return cptr. Could probably do some other things. But I hope I could give you a good impression on what it means to write your own monad. Because writing monads is actually not magic, although they seem to do magic stuff. It's actually not even a lot of code. It's just template code. So general advice for template code applies. In this last section, I'd like to show you one more thing. We have seen how monadic operations are useful on their own, but you can also combine them. So what I'm going to show you is two more monads, and then how you can combine them to profit even more. Since we are a bit late in the talk, I will not go into the details. I will show them mostly conceptually. I still hope you can get the gist of why you would use them and whether you want to maybe explore them after the talk. And you will find, as always, the code and material behind the link at the end. So again, we have a pipeline of tasks, and this time they are slow, like really slow. We're not gonna want to block on that, are we? So what's the alternative? We can use the continuation monad. The continuation monad allows us to specify a pipeline up front, non-blocking. Our results get wrapped in the future, and the future will start computing the results in a separate thread. This way, our calling thread is not blocked. When the first future is finished, it will trigger computation of the second future. Again, monad magic comes into play because the second function does not get a future as input, it gets an unwrapped future, it gets the result. So again, we have an unwrapping that happens here. We can use the same functions as we used for the vectors or optionals or whatever. Of course, the functions need to be thread safe. Since they are pure, we are good. There's not really a continuation monad in C++. There might be something similar in C++ 26, but from what I've heard, it's not really monadic. And anyway, I want to show you something that you could use today, right now. And the best and most production-ready library that I know of is Qt Concurrent from the Qt framework. And you can use it starting with C++ 17. So we start our pipeline with Qt Concurrent Run. And Qt Concurrent Run takes two parameters. The first one is a callable that will be called in another thread. And the second one is the initial parameter, the initial value. We continue with the pipeline with then, very similar to the end then we have seen before. And our result is the future to the final result. Now, we could do many things with that future. We could query the status. We could cancel the operation. I do the simple thing and block until the future is ready. But what about tracing? Because I might have multiple such pipelines running in parallel, and I want to have a nice trace of each of the pipelines. And I also don't want to have like a global mutex. And how could I do that? Here we come to the second monad, the writer monad. The writer monad makes tracing part of our call chain. So how does that work? We construct the writer object and pass an initial value into it. It's a template class, again, so it can take a value of any type. When we get into the first stage of our pipeline, we call end then, and this time I gave end then a second parameter, which allows me to add trace information to that pipeline entry. As you can see below, the trace entry goes into the wrapper, into the writer wrapper. And then we will repeat the same thing with the second pipeline stage, and we collect even more tracing. At the end, we get both the result and our trace information. And if you want more flexibility, you can change your functions to already return trace information. That way you can trace input parameters, intermediates, whatever you like. And the pipeline also got simpler. We just passed the functions. You can combine both ways. So for more involved stages, you use this one. And for the simple stages, you just use the other one. And now we combine both monads, the continuation and the writer. This needs a little glue to work, because Qt Concurrent Run expects a function and an initial value. So I create a simple make writer function, which accepts the initial value and constructs my cWriter object. That then now needs a function that understands the cWriter API. So I wrote a little adapter function which creates the correct API from an existing function. It basically wraps the function. This way I can pass my functions through the pipeline. And as a result, I get a C writer of string, the string being my final result. And again, the C writer containing all the trace information I collected on the way. So on one hand, you have the continuation monad, which allows you to easily offload tasks into separate threads. On the other hand, you have the writer monad, which allows you to make tracing part of your pipeline. When you combine them, you get log-free per pipeline tracing. I think that's pretty nice. Of course, you can also combine the writer with other monads like ranges, optional, expected, if you want to know exactly what your pipeline does. I'm coming to the end of this presentation, and I hope I could give you some ideas what functors and monads do, and some concrete and useful coding techniques. We have seen how functor magic works on a value hidden inside some sort of wrapper and helps us avoid repeating code. We have seen monad magic do the unwrapping, allowing us to build pipelines we could not build with functors alone. And we have seen the benefits of pure functions and why you should decide them in your code. If you have known this before, I hope it was still a good reminder and maybe I could fill some gaps. Of course, there's much to explore, and if you follow the link I'll share in a moment, you will find plenty of further references to follow up on. If you were new to this topic, I'd like to remind you one last time on what you can do right after this talk, what you can try out. And that are the monadic operations of the standard library. The ranges view monad if you have a pipeline where each input creates n outputs. The optionals may be monad if you build a pipeline where any of the functions might fail to provide a useful result. Alternatively, std expected if you want to provide useful error information in case of failure. And optionals default monad if you just want to grab the first usable result from a series of functions. These will help you write safe and readable code, the monadic operations of C++23. And now for the promised link. And I don't know how you hold it with questions around here, if there are any. Yes, do we have a second microphone maybe for the audience?
Hi. Thank you, very interesting talk. A question, when we go back to the slide when we created our pointer-based monad, and
wait a second. So the pointer-based monad, yep.
And we were implementing the...
Okay, let's jump to the implementation. Which part specifically?
We implemented the and then.
The and then, yes.
Mm-hmm. So here, the return type is, one case it's a pointer, and the other case an std optional. Mm-hmm. How, since when can I have a function which have two different return types?
Well, basically, it's a template function. So I will get different code depending on what invocable, on what function I pass in as input parameter. And the function I pass in defines my return type. So basically, I generate like, okay, let's say I have two functions. I have one function which returns a pointer and one function which returns an optional. Now, if I use those two different functions, I generate two different implementations of this template. One which returns a pointer wrapped into my CPTR, and one which returns an optional. I think that's kind of the nature of a template function. Here, it also influences the return type, but since it's not the same function, that works.
Thank you.
This is, yes, I forgot to explain the if const expert because it's C++ 17. And it's like, for me, it's so many years in the past now. maybe I should say a word on that, because what it means that this if will not be evaluated at runtime, it will be evaluated at compile time, which means the whole function will either have this block or this block or this block, but never all of them. So I create different functions with different behavior depending on my input types.
So going back to the classic example of the int-cell negative.
Int-cell negative, the optional, yep. The classic implementation, something like this.
Okay. I was just wondering if I replace this with 3 or 4 and thens, does this function, if the first step fails, it'll just do one check. Is the return element equals null pointer?
Yeah.
Will the monadic version do just one check, or will it check optional 4 times?
So let's look at the monadic version. Well, actually, I think that one is useful.
Yeah, that's
the best slide for that. So yes, it has to go through. I have not made like benchmarks. I could imagine that this might be a problem in very performance sensitive code. On the other hand, I can hardly imagine that most compilers will not optimize a lot of that away, because they can basically, well, they cannot determine at runtime, but it's they have to, like, you will have a few more branches, that's for sure. Well, the compiler, what I don't know is if maybe the processor will optimize some of that with branch prediction. I don't know. But I really have not looked into the performance of these things. I know the performance is solid. If you need the last 10% of performance, then you might want to check this before you use it.
So thank you a lot for the talk. I enjoyed it. I have a kind of provocative question. So the US government now urges developers to stop using C++ code in critical programs. And don't you think that the functional programming and actually views in particular and lazy evaluation aspect of views in particular introduce way too many hidden ways and insidious ways to get use after free issues? And this is essentially, as far as I know, one of the reasons they are banned now in the Google style guide.
Okay, so multiple answers to that one. First, it was under the Biden administration when we got all these reports. Nobody knows what the Trump administration is going to do. So that's one point. The second point is, yes, the ranges view is problematic in some ways. The parts that I have shown you with transform and join, if you keep an eye out for the laziness of it, are, I think, pretty okay. When you go into filter view and those things, then it gets really tricky. And honestly, I hesitate to recommend ranges views to developers who don't have a rather good idea what actually is going on. That said, optional is and expected are different beasts, because they are not lazy, they are eager. So you don't have those problems. So I don't hesitate recommending optional and expected. But thank you. it's a good point. There have been discussions on making ranges views also safer, but as always, backward compatibility bites us.
Thank you so much. And another, sorry, provocative question, if you let me. In the past, I was advocating a lot about declarative design and functional design in C++, especially after watching and talking to Ivan Schimkowitsch, watching his talks. Yeah, but I ran into a lot of pushback from the developers, and mostly because the code doesn't actually get simpler to read, because you get like a lot of visible noise from lambdas, and also it gets usually less performant because you try to use, you try to be on the safe side, you try to use pure functions more, and which introduce copying and so on. So in the end, you actually end up with a bit more cumbersome code and with less performant code. So what would be the argument against this pushback?
Well, I think there's multiple ways to view this. One way is, okay, depends of course on your team, whether code like this is accepted in your team or not. It's probably a matter of discussion if you really want it. In my case, I know that only a few of my colleagues use this kind of code, but they accept that I write this style of code in my parts of the code, and they review it, and I can explain it, and they understand it, what it does, basically. The performance aspect now, I think it depends on how performance bound you are, because personally, I'm the lucky guy. I work on desktop. I have loads of memory. I have 32 cores, and most of them are idle most of the time. And I just need to make sure that I don't get quadratic complexity or something like that. And if it's like 10% slower or faster, personally, I don't need to care. I'm fortunate in that. I understand if somebody has very tight performance requirements, this might not be the right code for them. If they want, on the other hand, maybe one day the compilers will be able to understand this code better than this code because it gives them more hints on what to optimize on. So I couldn't say. I think a talk about the benchmarking and performance characteristics of classic versus monadic would be a nice follow-up. Andreas?
Thank you.
Yeah, I have opinions, especially on like this last point. I actually completely agree. Like if with this example, right, you do one thing, then you do the next, then you do the next, and if any fails, you just jump out. The first code is fine, right? It might not be great, but it's fine. You won't get into trouble, right? Where it gets interesting is if the control flow becomes so complicated that it gets challenging to see what's going on. And I think this is like what this working with monads can teach you, is that they show you how you can abstract like matters of control flow away into their own structures and how to decompose it that way, right? So you have on the one hand, like you have the individual computation steps, and on the other hand, you have the control flow. And now you can separate the two. And if you do that right, and it's hard to do it right? But if you can do it right, then very often the problem becomes considerably simpler, right? Because like solving the control flow problem in isolation is easy enough that you can like directly see, like you can understand what and then does in isolation, right? It's a very straightforward thing. And similarly, you can understand the individual computation steps in isolation. But when you combine the two, then things might get messy, right? And I think that that's really the takeaway, right? Like, and monads is just one framework in which you can do this. Senders receivers in C++26 is a different one. But like understanding how you can like separate concerns like this, that's where the true power lies here. And then, yeah, of course, there's always caveats and trade-offs, right? So it's there's no perfect solution, but I think it's a powerful tool that's worth understanding.
I definitely don't want to like bring everybody to this style of coding. What my goal was is that you will be interested to try and see if it fits your use case. And if it fits for 1/3 of you, that's a great result for me. Yeah. Just a comment from the off. It's not wrong. It's
I have a question. Wondering how does the monadic stuff has impact on compile times?
I would, okay, again, this is not something I mentioned. Performance was not, neither compile time nor runtime was an aspect of my talk when I created it. But I would expect that the monadic version is slower to compile than the classic version.
Shortcut. Thank you for your talk. Can you say something about the combination functions and standard async? Maybe it's not a good idea, I propose.
I'm afraid I don't know enough about async to comment on that. Sorry. Okay. I think I see one more in the back.
So thanks for your talk. I enjoyed it a lot. I was wondering, like in the initial example you did when you started your talk around tree traversal, I was wondering the efficiency, and that is kind of like in the same direction as the performance stuff we already heard.
This one?
No, there was right when you started it. There was this
yes,
the sketch you had.
Just a sketch for
Yes.
the. Wait a second, for the monad theory. This one with
Yes, it is perfectly fine.
yes.
So what I was thinking, like if you have a tree structure and you're starting to traverse it and you're trying to do that with a monadic style, what you end up with is having a load of reallocations, because basically for each level of your tree, you need to allocate new vectors, right?
Yeah, if you do it like that.
Exactly. So what I was wondering, like, let's say traditional imperative style.
Wait a second. We are here working with ranges views. So if I just show this part
Yes.
of the, so basically we start with a vector, okay, and the rest of it is for the moment just an idea. The view is an idea. There's no data actually in it yet. Only when we start iterating and fetching data will it actually do the transform, the join, the transform, the join, and give me the first item.
Okay.
So it will build up the data as we go along. Now, I have seen a talk from Google, and somebody mentioned it, presenting their library called Readable, which unfortunately I believe is still not open sourced. And their motivation was that the ranges views has very bad memory characteristics if you have huge pipelines. So maybe this is something you are getting at.
Well, I was wondering, like, what would be from a memory point of view, like from an allocation point of view, the ideal way to traverse this, to flatten that tree. Like, you could just iterate it, like in a pre-order, whatever, and you could try that. Probably you need to grow the vector in a more straightforward way. And I was like really curious about what the memory characteristics are using that approach.
Yeah, another thing to test, because actually in the view it would only ever need to generate one item at a time. It doesn't never have to store all of them.
Exactly.
But still, from the talk from Google, I got some numbers that were not looking so great. So I think, again, this is something that would need some testing.
I guess likely it depends on how often you have to grow the vector. Yeah, okay.
Yeah.
I accept that there's no real test data here.
I have no data for that. Sorry
Okay, thank you.
about that. Okay, shall we wrap it up here? Yeah. Then, thank you again.